So for chapter 4 is about exponential functions. Today our focus is going to be on growth and decay. And we're going to be graphing and we're going to be identifying different situations with growth and decay. All right, so there is a standard equation for an exponential function, so that's what we're going to put in the box. When you are writing an exponential function, the x is the exponent, so you do need to make sure you write that a little bit smaller. And you could see it with an f of x equals, but that b is going to be the base. Okay, so what do the variables in the equation represent? B is called the base. The exponent is a variable. Most of the time, that variable is x. In other models, it may be a t, because t is going to stand for what? What does t usually stand for? Time. Yep. All right, now, some models, there's going to be a value in front of the base. That's called an initial value. It is also the y-intercept on the graph. So we're going to keep that in mind as we are graphing. Okay, and when we're thinking about exponential functions, we want to think about, like, what are some actual situations that we can use exponential functions to model? Can you guys think of any? Can you think of anything that grows very rapidly? Okay, yeah, like stocks, right? Money. Again, with the money, right? Anything else? Okay, sometimes, yeah. Population growth. What about that? There's definitely some things with the climate, and there's definitely some things with the environment. Did some of you do exponential functions in biology last year? Have you done anything like about the half-life of organisms? Okay, because that would be exponential decay. What's something big that grew very exponential?
COVID.
What's that? Oh, well, not exactly exponentially, but yes, disease. Okay, so disease can absolutely grow exponentially. Many times we'll see quantities double. Okay, so sometimes a quantity will double or triple. Okay, and so you can write down any of those that we just talked about, right? So there's situations with money. There's situations with disease and population. Those are all great examples. Okay, and then when a quantity doubles, you are going to have a model where the base is 2, and then sometimes you'll have an initial value. A lot of times that initial value is 1, right? And then if the initial value is 1, you can just write 2 to the x. Or sometimes you might have something that triples. Okay, so you have y equals a times 3 to the x, or just 3 to the x power. Okay, and then now we're going to get into some of the fundamentals about growth and decay. Okay, so a lot of the things that we're talking about today are going to lay the foundation for different concepts we're going to talk about later in the chapter. Today we're going to be doing some more basic models, and then, like I said, as we continue on in the chapter, we'll expand those. Okay? So when we talk about the fundamentals or the basics, we want to make sure we really understand what some of these words mean. For example, you can see in the next part, I'm asking you about the domain and the range. So we're going to talk about that. in detail today. Okay, choosing any more time with this one because I'm going to switch it over. All right. So the next one asks, what is the parent function for the exponential function family? We are going to draw a sketch of it. Okay, and then we are also going to state the domain and range, but we're going to talk about that in depth first. Okay, do you guys remember what the domain and range are? What? Yeah, a lot of times it is all the numbers, but why? Wait, can any of you tell me what the domain and range are? Okay, so what is corresponding to the y's?
Like the actual function.
Well, it is going to be the y's of the actual function, okay, and then, but that y's go with which one, the domain or the range?
Range.
Okay, yes, it is the range, and then the domain is going to be the set of possible x values. Okay, so I think it is good that we're going a little more in depth on this today. So when you are trying to think about the range and think about the set of possible x values, basically instead of thinking about all the x values you can have, because a lot of times it's an infinite amount, what you really want to look out for are the restrictions. Okay? So the things you want to look out for are those different calculations where you get an error. Can you guys think of any time where you try to do a calculation where you get an error on your calculator? Well, what is it?
Divide by 0.
Okay, yeah, the first one is dividing by 0. And then Dave, we're going to come back to yours. So so you want to look out for fractions because you can't divide by 0. Okay, so fractions because the denominator cannot equal 0. And then, Dane, you said something about negatives, right?
Yeah.
Can you elaborate on that?
I don't think it's right.
Well, there is a situation that we can't have a negative in. Can you guys think of it? Well, yeah, that would be doing what? We can have negative exponents. We'll talk about that. But the imaginary numbers come from doing what with negatives? Okay, so take the square root. So you have to also look out for square roots because you can't take the square root of a negative. And there's one other thing eventually that we're going to look out for, but we're just not ready yet. So we're going to save that. Okay? All right, so the domain is going to be the set of possible x values. Notice it's possible. What is possible that you can plug in and get an answer? Okay, so when it does say the set of possible, you want to think of your restrictions. Okay, restrictions are values for x that do not produce a valid answer. And that is rare, okay? We've only talked about these two situations, right? So you couldn't plug something in for x that would make the denominator 0 because you wouldn't be able to get an answer, right? You would get that error, you can't divide by 0. Same thing if you try to use your calculator to take the square root of a negative, okay, you would not get a valid answer. You'd have to go into your imaginary numbers. And then, oh, sorry, I just said set of possible, but we got to put the x values. All right, and then we know that the range is the set of possible y values. Okay, and the set of possible y values, the simplest way to find that is to look at the graph. Okay, so the set of possible y values, we are going to use the graph to find the lowest to highest y values. Alright, so like I said, these are foundational things that we're going to build upon as we dive deeper into the chapter. Okay, so we have the domain and range. We are going to talk about the equation. So for the parent function, you are going to have y equals 2 to the x. Is it just going to be a couple minutes?
Yeah.
Yes. Yeah, Grace and Dave. Okay, and then y equals 2 to the x, that's your parent function. So if it doesn't have a fraction or if it doesn't have a square root, your domain is going to be all real numbers. And then the range, we are going to use our graph to do that, okay? Okay, so we're gonna draw a sketch of this function. I was just thinking about where I want to squeeze it in. We'll do it here. Okay, so what we're going to do is we're going to think of this as -2, -1, 0, 1, 2. Now, some of these you're already going to know right away, because if I were to plug in 0, what's anything to the 0 power? 1. 2 to the 0 is 1. What's 2 to the first power? 2. What's 2 to the second power? 4. Now for these, do you guys remember what happens with your negative exponents? It's a fraction. This becomes 1 over 2 squared, which is what? 1 over 4. So if it's -1, 2 to the -1 is 1 over 2. And it's okay that that went there. The graph isn't going to go there. All right, so let's graph this now. So 1, 2, -2. So I have to go up to 1, 2, 3, 4. 1, 2, 3, 4. All right, and then when we graph, let's go ahead and graph this side first. So we have 2, 4. And then at 1, you are at 2. At 0, you're at 1, because remember, that's going to be your y-intercept. And then here we have 1/2 and then 1/4. So what happens with these graphs is they get closer and closer to the x-axis. Okay, so draw your arrow, and then draw your arrow here. Okay, as it gets closer and closer to the axis, there is an invisible line there that has a special name. Okay? We'll practice saying it. It's called an asymptote. Okay, so asymptote. Ready? 1, 2, 3. Asymptote. Isn't it fun? Okay, so the definition of an asymptote, it is a line the graph approaches but does not cross. So it's a line the graph approaches but does not cross. And that is specifically for exponential functions. I'm going to put that in a different color for exponential functions. And that happens as the value of x gets very large or very small. In this case, it gets very small because as you see, like the -3, -2, well, you have the -2 is 1/4, -3 would be 1/8, and then 1/16, 1/32. So it would keep doing that, right? And it would never reach 0. So we call that an asymptote, and it is going to be a horizontal line. Okay, so it has a horizontal asymptote that the graph will never cross. Okay, what is the horizontal asymptote for the parent function? Label it above. So what is it getting really, really close to? Yeah, it's getting close to the value of y equals 0, which is, I heard one of you start to say it, the x-axis, right? Okay, so when you draw this in, you are going to use a dashed line. Okay, that shows you that it is not physically part of the graph. I usually use a highlighter because I feel like it's hard to see it otherwise. So you can do the same, or if, when you're doing your practice, if you want to do like a different color pen just so it shows up, that would be fine. Okay, so you definitely want to use something where it's going to stick out. Okay, and then we're going to talk about your growth and decay models. So with exponential growth, you can tell right from looking at the model if it is growth or decay. Because if it is exponential growth, it's going to have a special value for b. And we're gonna talk about both of these situations. And decay, again, it's the same model, but there's going to be a special stipulation for b. Okay, so for the exponential growth, it's going to be where b is greater than 1. You guys remember what rule that's similar to? In your transformation? Yeah, the vertical stretch. Yep, good. For the exponential decay, what do you guys think it's going to be? 1. Yes, I knew you would think that, but that is not true. So, but that's very common to think, right? We think decay, it has to be negative, but that's not true. Things can grow very large in the negative direction. For example, the national debt, right? So it's growing. It's just growing negatively. Okay, it's growing in the negative direction. But if it's decay, it has to be getting smaller, which means the value of b. Do you guys want to take another guess? It's going to be less than 1, but also what? Greater than 0, which is very similar to what we talked about with the compression, right? Okay, so let's look at a couple of examples, and what we're going to do is we are going to draw some very rough sketches. Okay, so an example of growth would be like y equals 5/4 to the x power. So even though it is a fraction, it is larger than 1. And then, like I said, we are doing just a rough sketch for this. It would look, this is going to be the shape. And then from left to right, this would be going up to positive infinity. So we're going to notate that. I'm going to draw a better infinity there. Okay, But like I said, it could also be negative. So you could have something like y equals negative 3 to the x power, like this. And then the graph would look like this. And from left to right, it would be going further and further, and it would be approaching negative infinity. Okay, so if it's growth, it's either going to be going to infinity or negative infinity. Okay, and then if it is decay, we're going to look at what some of those look like. Here would be an example equation, y equals 2/3 to the x. Okay, and then you would have something that looks like this. Okay, now from left to right, this is going to be getting closer and closer to the value of y equals 0. It's approaching that x-axis. But you could also have an equation like y equals negative 2/3 to the x, like this. And then that's still going to be approaching y equals 0. It would just come from the other direction. Okay, so it would be getting closer and closer to y equals 0. So that says y equals negative and then 2/3 to the x. Alright, so how can you tell the difference in the equation? What about in the graph? Well, we already talked about how you can tell the difference of the equation. When you're looking at these, you really do need to look at the absolute value. So that's what we're going to talk about here. So how can you tell the difference in the equation? What about in the graph? I'm going to put up what I have for you. Okay, so for decay, the absolute value of the base is between 0 and 1, whereas for the growth, the absolute value of the base is greater than 1. So again, you do have to take that absolute value into account, because a negative is not going to make it decay. Okay, it depends on where it's approaching. Okay, so for decay, the absolute value of the base is between 0 and 1, whereas for growth, the absolute value of the base is greater than 1. Now, what about in the graph? So with both of our graphs that we did up here, we talked about what it's approaching. So if it is a graph of decay, both of these happen to approach the x-axis. That's what we're working on today, the fundamentals. But really, that x-axis in both of these cases is the horizontal asymptote. Okay, so decay graphs are going to approach the x-axis or the horizontal asymptote from left to right. And this is something, like I said, today we're doing the fundamentals, we're getting those basics down, and then we are going to expand those. Now, if you have a graph that models growth, that is going to approach either infinity or negative infinity from left to right. Okay, so when I say from left to right, I mean you have to look at the graph starting at the left and then seeing where it's going on the right side. So this is approaching infinity, this is approaching negative infinity, so that's going to be growth. Whereas the decay is going to approach their horizontal asymptote. Okay, because you might have to say whether it's growth or decay just by looking at the graph. And you wouldn't have the equation. Okay, so you have to be able to tell from either one. Now, a lot lot of times when we talk about growth and decay, we have different models that are going to fit some real-world situations. And you'll have to tell me, you may have seen these before in Algebra 1, if you would. Are you awake right now? All right, so the growth model is y equals a multiplied by the quantity 1 plus r to the power of t. And then in that growth model is something called a growth factor. Okay, and that is going to be that quantity 1 plus r. Now, in some cases, when you're doing a model, you might have a doubling situation. If you have a doubling situation, you don't have to worry about this 1 plus r. You can just use y equals a times 2 to the x. Which really makes sense because if it's doubling, right, you have 100% and that is doubling another 100%. So the 1 plus 1 would be the 2. Okay, that would be the doubling. Okay, you guys actually already probably know what some of these variables mean, but we are going to go over them, and they are also going to apply to your decay model. So your variables, your y is going to be your final amount. Okay, a lot of times you think of that as your final answer. Your a is the initial value, so we already mentioned that today, that the a is the initial value. The r is your rate. Your rate is expressed as a decimal. So many times your rate is given to you as a percent. Do you guys feel like you're comfortable turning those into a decimal? The percent? Really, it's just you divide by 100. When you divide by 100, what do you do to the decimal? Yeah, you move it 2 times to the left. Okay, and then t is time. This is a 1, so this 1 here represents 100%. Okay, so the 1 represents 100%. So you're going above what you already have. All right, now you'll notice the decay is almost identical, except instead of 1 plus r, you have 1 minus r, and that is also going to be your decay factor. Okay, so if it asks you what the decay factor is, you would actually perform the 1 minus r. If you're asked what the growth factor is, it is going to be the 1 plus r. Okay, and then once you have that written down, I want you to flip it over, and on the back I want you to see if you can identify whether those are growth or decay.